intellectual tradition of excellence and quality and devotion to heavy element research continues in Berkeley. Jen Greiterich is co-leader of the heavy element nuclear chemistry groups in Berkeley, a significant contributor to understanding the chemistry of these elements, which really does change our perceptions of some of the things concerning the periodic table, and has in fact been the leader of a recent experiment which has gotten a lot of interest, etc. and so forth. So Ken, you're going to talk on discovery of the long-sought super. Mention one thing. You were out running this morning for how long?
About 4 hours and 20 minutes.
How far?
That's 50 kilometers. In the bus. Need some more fun. Okay, I was going to tell you about we have the elements, discovery of element 118 and element 116, but I have to start out with the periodic table. I'm a chemist, and so the periodic table has to be here. Periodic table, this is colored for chemistry. Right now we're talking about element 118. 118 is supposed to be underneath radon. I only filled in the elements which we study chemical properties for, but element 118 is supposedly belonging here below radon, 116 below polonium. But each of these elements has can have a different number of neutrons in there, which makes a different isotope. It has different nuclear properties. And so the idea of the super heavy elements has been around since the late 60s, early 70s. Here's some early calculations. This is taken from Steve Roach's book. The name of the book is Elements Beyond Uranium. It shows some early calculations. And what it shows is this is the proton number or the atomic number of the nucleus along this side. And the number of neutrons in the nucleus goes along here. And these are contours that show either decay energies or half-lives or shell effects. And basically the center of all these concentric circles or whatever shows increased stability. And it's pretty consistent that it shows a neutron number 184 or 180 in this case. There's enhanced stability. And also around element 114, 116, or 1, well here they'll show 116. And so this idea has been around for a long time. There's been a lot of searches for these super heavy elements. And just in the last few years, there's been some success. Both here and in Dubna and the people at GSI really kind of paved the way showing us how to do these experiments. In a more simplified view, this is from Adam Sobieszewski, a theorist from Poland. This is kind of the way people thought it was in the 70s. Here we have stability in the actinides and the heavy elements that we know down at the bottom of the periodic table. And there was kind of no stability in between here around proton number 112. And then the prediction of super heavy elements, an island of stability. And people are asking me these days, what do you mean island of stability? Because this is what it looks like today. The elements, the heavy elements, actinides and so on are down here. But there was found, the theorists predicted using some higher order deformations or different tricks in their calculations. They said, oh, look, 162 neutrons around 108 protons. There's increased stability there too. And about, within the last 10 years, that's been pretty well confirmed, and a lot of experiments that have been done that show this is really the case. It gives us more confidence that these old predictions of super heavy elements are also correct. So, the way these reactions go, they're nuclear reactions. And so these balls are not atoms, these are the nuclei of atoms. For example, for the 118, at the 88-inch cyclotron here at Berkeley, we accelerated krypton 86, and we used a target of lead-208. So it's krypton that's got 50 protons. It's got 36 protons and 50 neutrons, and lead-208, 82 protons and 126 neutrons. Sometimes, very rarely in these reactions, the krypton 86 nucleus has a central collision with the lead-208, and then when that occurs, once in a great while, they fuse totally to form a compound nucleus. This is just a total fusion of the two nuclei. They equilibrate their excitation energy, and you end up with an excited compound nucleus. It has extra energy in it and it has to get rid of it. And what we're hoping for is that it would de-excite by emission of a neutron. Just to help cool it off so that it's stable. Most of the time, however, it falls back apart into two fragments of more or less equal size. And so, in a very rare case, we form an atom of element 118. That's what we've been trying to do. This is a picture of some results from GSI in Germany. They've been doing reactions like this compound nucleus reactions for many years. And it shows us a clear systematics that as you try to produce, this is the cross-section or production rate, and here is the atomic number of the final product. And it shows very clearly that as you try to make heavier and heavier elements, the production rates decrease. There's some effect with neutron numbers, so there's some lines going over. But if we put the krypton 86 plus lead 208 on here and do this kind of extrapolation of this slope, we end up with something over here at the red dot. Well, this corresponds to a production rate of about 1 atom per week. And so if you come down here, you're getting into the atom per year kind of range. So it looks really difficult. But we have here at Berkeley a visitor, Robert Zalonchek. He's, again, from the same institute in Poland as Adam Sobieszewski. He actually worked under Adam Sobieszewski. And here he's been doing some calculations about these fusion cross-sections and the heavy element production. And he found some interesting things. He said, okay, if you do krypton 86 plus lead, like it shows at the top there, at this energy, 149 MeV is the energy of the krypton from the cyclotron. He predicted 670 picobars. And we go back to the other picture to show you where it is. Okay, 670 picobars would be at about this level, about this level. Way up here, production rates of a whole bunch of atoms per day. So we said, Robert, how serious are you about this? And he said, well, maybe factor of 100. Okay, he went further. For many years, he and the group in Poland has been doing mass calculations of nuclei. And from those masses, you can predict the decay energies if they're decaying by alpha decay. And from the alpha decay energies, you can also predict what the half-lives should be. So the idea is, okay, 118 should have a decay energy around 12 MeV and should have a half-life around 100 microseconds. It decays to 116, which is also radioactive. It likes to emit alpha particles, or prediction was. A little bit lower energy, a little bit longer half-life, and so on, through 114, 112, 110, 108, and on down to 106. And then by the time we got to 104, Robert said, okay, we should fish. And so that's what we were looking for. For the past 3 or 4 years, we've been building a new device at the 88-inch cyclotron. It's called the Berkeley gas-filled separator. I'll talk more about that in a minute. We see somebody who should look familiar right now, but also Victor Ninoff has been working with us for the past 3 years, putting together the BGF. And so this shows the device. It was actually made out of some old magnets that we dug up on the Bevel-Act floor. This is an accelerator at Berkeley, which was closed down in 1993. We took some old ugly magnets, refurbished them, made modifications, and put it together into a separator that at this point we think is really the best in the world. Okay, now I want to talk a little bit about how it's supposed to work. Okay, the 3 blue magnets that you saw in here, here's the first one, it's quadrupole. The next one behind it is right here, and then the third magnet, which you barely see in the picture because the other magnet is away, is back here. The beam would enter from this side, and this is the target position. What we have for a target is a wheel. It's about this diameter, and the targets go around the circumference of the wheel. And the idea there is, when we're bombarding with the high-intensity krypton beam from the cyclotron, it produces a lot of heat. And if we just had a target sitting there, it would burn up. So what we do is we rotate this wheel at about 500 RPM. That spreads the heat out around the whole circumference of the wheel. It gives the target a chance to cool so we don't burn it up. We have some detectors here for monitoring the beam intensity, just to tell us how the beam is doing. But the interesting thing is, now, if we have a compound nucleus reaction where the krypton nucleus fuses with the lead nucleus, this 118 recoil gets knocked out of the target, and conservation momentum says, okay, now this 118 has the momentum that the krypton beam had. And so we take advantage of that. We send it through these magnets, which are set so that they focus the 118s over here to our detector area. And with the gas field separator, we get higher angular acceptance, higher velocity acceptance, and everything. But another bonus is, most of the time, the beam goes through the target without interacting, and we got to keep that away from our detectors because it would destroy the detectors. In the vast majority of the cases where there is a nuclear reaction, we make something other than the 118. We need to get those and keep those away from the detector. And it turns out that all these other products tend to bend easier in a magnetic field, so they take a smaller radius and they curve out of the way and they crash into the side of the separator over here. And we have the 118s coming all the way through to the detector box. And I can show you what the detector box is looking like now. So here we have the 118 is supposed to come from the separator through this way. We have a transmission detector here. So the 118s can pass through and leave a signal. I have another picture that's more simplified. The second transmission detector, we can measure the time difference between the two to get the velocity. And then here we have a focal plane detector array, which is actually the heart of the detection system and allows us to make these identifications based on something like production and decay of 1 atom per week. So here's how the detection works. These are the elements that I showed you, and there we have a transmission detector, and the second transmission detector. It flies through, we measure the position and the time here. Also here, we can take the difference in the times, and that gives us the velocity. So we can say, okay, this is something in the vicinity of element 118, because the velocity is set. And then we have what's called a silicon strip detector. And so this 118 comes in here, hits the detector, and in that detector we measure the energy that it came into the detector with, we measure the position and the time. And as I showed you before, this 118 atom decays by emitting an alpha particle. The 116 daughter also emits an alpha particle, and so on down the line. So what I show here is it's sitting inside the detector, inside the silicon somewhere, and these alpha particles are coming out. And we measure the energy and the time and the position of those alpha particles. So basically, we're looking at this position where we saw the 118 recoil come in and watching for alpha decays at that position. About 60% of the time, the alpha particles go into the silicon. Sometimes they come back out in the backwards direction, and we detect only a partial energy and they come out. One of the new improvements that we've done with the BGS is we put some detectors around the sides here to try to catch these alpha particles that are coming out so we can still measure the full energy. That's really